All right, so let's recap a bit before we start the next part. We have already done quite a bit. Okay, so we created a set of core interfaces, right? We've got our linked list and our iterator. We created a default implementation of both, a single-threaded circular doubly linked list and this companion iterator implementation back over here, right? And then we tested this implementation and in the process figured out how to create repeatable automated unit tests and measure their coverage using Go's built-in tooling. And then we created two more abstractions that leverage our linked list out here in our queue and our stack. Great. Now we could have put the interfaces for queue and the stack in base.go here as well. And there's nothing wrong with that. In fact, that's probably the better thing to do. But I chose not to since I'm not going to include any more queue and stack implementations. To be strictly correct, I probably should have thrown that in there. Now, the cool thing about Go is we can go ahead and create an interface for each later if you want to, without having to touch the implementation here at all, as long as the interfaces you're creating do retroactively, fit what we implemented here, and they're compatible with that. So that's the cool thing about Go. So if in the future, if we choose to have more queue implementations and we want all of them to kind of be compatible with this one base interface, we can just extract that out, write it here without ever touching an existing implementation. And that is just awesome. Okay, and finally we figured out how to run tests and measure their coverage for an entire directory structure containing Go files in one Go, pun intended there. But we did that using this testall.sh script here, right? So, just a quick thing, this script that I've written, not that I'm going to be pushing it on you, I'll probably be using it until I find something better. But this is guaranteed to work. If you just drop it in some directory, you can just run this. It does not have anything specific to my project that I can tell here. So feel free to use this script if you want to. You probably have something much better than this once you get going. So it's there if you need it, right? Anyways, so what's next? I want to start scratching more surface off the OOP support in Golang. We really have only scratched the surface there, right? I want to go deeper. And let's see how things like inheritance and polymorphism, really the cornerstones of OOP, look like in Go. So to experiment with that stuff, I'm going to go ahead and create a new linked list implementation. I want this implementation to be able to heavily leverage the existing one we already have, with one small twist. I want the list to store elements in natural order. Now numbers and strings, we know the natural order, right? It's for numbers, it's 1 followed by 2 followed by 10 and so on, right? While for strings, like if you take names for example, it's always going to be Andrew followed by Jack followed by Saharsh, if you're doing alphabetical order, which is really natural order for text, and so on. And we can easily write the implementation internally for those guys. But I want the user to be able to specify the order of any type they might ever store in our list, right? Because that's when it actually starts being useful. So to do that, let's go and create an interface first. Let's go back to our base.go file, right? And we will expose this interface out through our base.go, and the users will need to implement this interface in the values that they pass in order to use the sorted list implementation. And you'll see how that works pretty soon here. And I'm going to shamelessly steal from Java here, and I'm going to recreate their comparable interface here in Go. Now, if you've done any Java, this should be super familiar, right? So let me just go ahead and type this out. I'll do the comment here in a second because I'm going to write quite a bit there. But basically, I'm going to create the comparable interface, and this guy just has one method, compare, which takes another comparable and returns an int. Well, what does this guy do? Now, if you have done any bit of Java, then this should be super familiar, right? You basically pass another comparable into this compare method, and then the method should spit out a 0. And let's write this down, right? So comparable describes things that can be compared. Let's just go with that. Why not? And implementations of compare should return, and this is how we describe it. Zero for equality, meaning the object that compare is being called on, or the struct that the compare is being called on, is equal to what's being passed in here, right? So that's simple. We'll have a negative integer if receiver is less than argument, and positive integer if receiver is greater than argument. Right. So yeah, this is basically, as I said, just shamelessly stolen from Java. And the method spits out a 0 if the two things are equal, a negative integer if the argument is greater, and then a positive integer if the argument is lesser or smaller. All right, great. So this is great. This is kind of a standalone interface anybody can kind of be compatible with in their types. But how do we use this? Okay, so for that, the list I need to create, before we get to that, the list I need to create needs to be able to inherit from my existing list, right? So that's the list that's actually going to use this as the interface that's imposed on the values being passed in. And that list is going to be my sorted linked list, right? And the sorted linked list needs to be able to inherit from my existing list and override the insertion logic so that elements are placed in their natural sorting order during the add operation. So what that means is we won't be able to expose the insert operation that our existing list operation exposes, as that would break the natural order guarantee. And everything else remains the same except the add operation that we are going to essentially override, right? That's what you do in a traditional OOP language. You would override, you would extend or subclass the list implementation and then override, basically provide another implementation for the add method. Now you would also need to hide the insert method, maybe throw like an exception or something if it's directly called in the subtype, because that's something that we cannot allow. But in Go, you don't really need to do that. Go doesn't do direct inheritance like your favorite OOP language. It has a strong opinion that composition is better than inheritance. But ultimately, Go does support inheritance, but essentially it's composition disguised as inheritance. So what does this look like? All right, so let's go ahead and create a new type. And now I'm not going to expose this type directly, but I am going to create its own file. So let's do that. So let's go back to the linked list package because we're going to heavily leverage this package again. We need to be able to get to the guts of it. So this new file is going to exist right here. And it's going to be just called sorted linked list.go. Easy peasy, right? Okay. And as I said before, it's going to be in the same package as the other guy, and you have to be because we're in the same folder. And the type, which is basically sorted linked list, I'm not going to expose. Because this is going to be my way of hiding the insert method. And you'll see why, because this is going to essentially inherit from the other linked list implements that already exist. So, and the way you do that in Go is you just basically do this. And this denotes to Go that you're essentially inheriting all the methods that's called on this guy, right? And that's all we need to do here. Because you're going to see we're not going to maintain any extra state here. All the state that this guy already has is enough. We just need to kind of circumvent the add method and hide the insert method. So how do we hide the insert method? We basically go in here, and I'm going to keep my public stuff up top, right? And let's create a func create sorted, which will actually return the base interface linked list. And this guy does not have the insert operation defined on it, right? It only has add. And so by only returning this as an exposed type here through create sorted, we effectively hide this guy because you can't directly use it anyways external to this package. And so insert method is hidden on anything that's a sorted list that you can only create using this method. So here we basically return our sorted linked list, and here we can call the normal create. This is going to evolve quite a bit, so I'm just going to leave the comment as this for now, and we'll, We'll get to it in a second here. All right, all my internal stuff is going to go down here, right? Great. Okay, so let's go ahead and add the add method that we're going to override. So how do we do that? So let's go ahead and get the signature right. So this add method is on the sorted linked list as opposed to the original linked list. And it's add. And add takes a value of any type, right? And doesn't return anything. It just adds to the list. So the first thing we need to do is we need to do a hard check to make sure that the value that is being passed in is a comparable. This type specifically is going to only support a subset of any type available, right? Instead of not actually supporting all interface types, it's going to only support the ones that also happen to implement comparable. But if I go ahead and change this to say comparable, it needs to be data structures.comparable. Then this gives me an error, right? Because it says I cannot return sorted linked list as type and return argument because it does not implement the add method. It has this data structures as comparable, whereas we want interface. So to be able to stay compatible with the base interface, we need to take in an interface type here, right? But then we come ahead and say, you know what, for this specific type, if you want to use this sorted stuff, you need to pass in a comparable. And we'll make that clear in the comment up here later on. I'm just saving that because it's going to grow in complexity, so I don't want to jump the gun here just yet. But we will absolutely capture the requirements to be able to use the sorted list here, right? So how do we go ahead and add the check to make sure they're only passing in comparable? Well, we'll do a downcast like we have done before. And this time we know the downcast will fail if they don't pass in something that's comparable, right, of the type comparable. And I'm okay with it just basically doing the standard syntax, or not syntax, but rather the runtime go error or the go panic, because the user should know what they're doing. They should have read my documentation. They should have known exactly how to use this method. So if they're passing in something that this method does not really support, I would say it's on them, right? Okay, so let's do that. And we'll call this guy C for comparable, right? Let's just call it comparable about that. Okay, and we do that by saying value and giving it the type comparable. We have the data structures here. And so this gives me the error that it's declared and not used, but this will essentially do that hard check for me. Okay. So now as we go about implementing this method now for the sorted case, we really have two cases that we need to worry about. The first case is that the list is empty. So basically we say, okay, if list.size is 0, and that should compile. Yeah, I'm not sure why the suggestion wasn't given to me, maybe because of this error right here. And else we'll do something else, right? So if the size of the list is 0, then we are just going to go ahead and leverage the existing add that already exists, and we'll just pass in our comparable to it, right? Great, and that makes it compile again. So this is our easy case. There's nothing in the list. There's nothing to compare to. We're just going to add this. This effectively puts things in the tail, but since there's nothing there, it's going to become the head and the tail, right? So we're happy there. Otherwise, we need to do some comparisons, right? So So in this case, now we can't really leverage what already exists as far as the nice abstractions, the nice exposed public methods of the linked list. And instead, we need to go into the guts and kind of come up with our own implementation using some of the more privileged or the packaged private types and logic that's sitting there, right? So how do we use that to our advantage? So what we need to do, we need to find the node internally that holds the value that comes directly after the value being inserted, and we need to prepend this value to that node, so a new node is created with this value, right? So that's something we've already done internally in this list, just not with this specific case in mind, right? So the first node we consider as a node to prepend is going to be head. We typically start at the head, right? And so that's easy. We'll just grab the head. Okay. And I'm also going to add this new flag in case the head is the node to prepend, meaning we don't need to go any further. Then if we prepend to the head, then we need to change the head to the new value, right? So I'm going to keep track of that by this flag. And I'm going to initialize it to be true because right now, as far as I'm concerned, the head node is the one that I'm considering to prepend. All right. After that, we go in a for loop because we're going to increment until we find the node, right? And here, we will leverage the compare method that the comparable has, right? And we'll pass in the value of node to prepend. And as long as, if this returns anything that's equal or greater than or equal to 0, that means the value here is equal to or greater than the value in here, and we're going to keep going forward until we find a node that's greater. And we can do this loop because we're always inserting in the right place. So the list after any insertion is always in the correct sorting order. So it is always going to go less low to high, basically, right? Based on whatever natural order you've selected. So this logic works because of that, and we can just simply keep going incrementally from head to tail until we find the node that works. All right, so in here, if we do enter this loop, that means the head is no longer going to be the one being prepended, at least not being replaced as the head, right? So we go ahead and set this flag back to false because head's not going to change. And then because this node is definitely not getting prepended, we need to change it to the next node, right? So we basically increment by doing this. Awesome. And then we'll put in a little break condition. So in case we have reached the end of the list, I'm sorry, list.head, jeez. Then we're going to go ahead and break, right? Awesome. All right, so what is this? And this is a safe cast because anything that's already in the list is going to be a comparable because of this right here, right? So anything that gets inserted is also going to be a comparable. Awesome. So after getting through this loop, we have now found our node to prepend. Worst comes to worst, it's going to be head again. We're just not going to replace it as the head. And then we go ahead, so we go ahead and insert it by calling our prepend operation. Then we declared a while back. And we simply pass in the comparable value. Awesome. And then if we are replacing the head, then we simply say list.head is now the inserted node. And this is the pain of not using the exposed interfaces and going to the guts of the list, because now we have to do all the internal housekeeping in this method. So we have to set the head if it's changed. We have to increment the size, make sure to remember that, right? Here we don't need to do that because this will increment the size for us. So after that, the add method is actually complete, right? Because add inserts value in the list at correct position based on natural order. And this should work. And we can prove that by adding some tests. All right, so let's go ahead and do that. Okay, so I've gone ahead and created the test for you. So again, you don't have to watch me type each line here. And what I've done is create a comparable compatible type. And I do that by first declaring this random struct called person, and then implementing the compare method on it. The compare method first asserts that both instances being compared are of type person. Then the comparison is done purely on the name field, and the age field is ignored, right? Now this way, the two people of the same name but different ages are considered equal. Now, I'm not saying that's the correct way to do it intuitively, and like that's how you would do it in some production code or anything like that. But I've done that because it will serve a purpose later. So that way, we can test a case where two objects are equal and what happens to them as they are inserted back in in some random order into the sorted linked list here. So that's purely done to orchestrate that case, right? Okay, so do the test. So the test is fairly straightforward. We add a bunch of people in seemingly random order. Then we go through and inspect that the elements are actually stored so that names are in alphabetical order. So even though we went through and inserted these guys in whatever way possible, we get them in alphabetical order. Adam, Bob, Candace, right? The interesting case here are the Joes. We insert two Joes. And the age doesn't really factor in the order. What really factors in is the insertion order. And we see, and then the age is just the way we can tell which Joe is, which. And as we expect, we inserted the 13-year-old Joe first, so we encounter him first as we iterate through the list here. We're not really iterating, we're doing random access here, obviously. We could have done the iterator, which would have been more efficient, but who cares, it's a test. And then the 18-year-old Joe comes later, and then everybody else is just in alphabetical order. Awesome. Then I also added another test to test that edge case where you try to insert something that's not a comparable. We definitely expect a panic since we put that guard in there right away. Basically, as soon as you come in here, it tries to downcast it to a comparable. This will cause the Golang to basically throw a panic and when it's trying to do this downcast. And that's the panic we expect to see here. Awesome. So let's go ahead and run this test. We can just run the test of the GUI first. We run all the package tests. We get 100% coverage as well as everything passes. And then just for illustrative purposes, we can do local test all, run our entire test suite, and we still have 100%. Obviously, we need to do the show HTML to get the HTML printout. And boom. So we can go out to our sorted linked list.go and see everything is covered. Awesome. So I'm still not fully satisfied here with the sorted linked list, and just for my curiosity and to kind of see, just to see how else we can keep pushing the language here. One thing I kind of don't like in my sorted linked list is that I have to make my callers always implement the comparable method. And that can be a bit burdensome if you're just dealing with some primitive types or something, right? So instead of doing this just a hard rejection of anything that's not a comparable, maybe we can build in some compatible type, or sorry, some built-in types that the list supports, and you don't have to wrap it in some sort of a comparable or implement a compare method on it, right? So how can we do that? So what I'm going to choose to do here is I'm going to go ahead and, in addition to supporting the comparable interface compatible types, I'm also going to go ahead and support a string, the string types, as well as just the typical int. I'm not going to go in and support every single uint, and I'll kind of moan about that a little bit here, or complain about that here. We'll make sure those are supported in addition to the comparable type. And what I'm trying to complain about that here is I just did not like the fact that, first of all, there's no generics, so I can't bound an instance of this sorted linked list to a specific type so that I don't have to leave it open. Like if you've done Java, you can obviously see that what you're really doing here is you're accepting an object type. If you've done Java collections or plethora of other libraries out there, you're probably familiar with generics. So you can instantiate an object that is meant to deal with objects of certain types, and you want to declare that, hey, for this instance, I don't expect it to take anything that's not at least a subtype of this high-level type or something, right? Or any type, really. And not having that is kind of cumbersome implementing a collection like this. Now, Golang's philosophy is generics are overkill, and they don't really provide a real benefit. I guess I don't agree with that, but at the same time, that's why different languages exist. If you really want that generic support, go do Java. Whereas Go is trying to keep things a little bit more simple. But you can see how code can be a little bit more cumbersome because you kind of have to do checks on making sure types are equivalent. You have to throw panics, things that would have really been caught at compile time in a language like Java that has built-in generic support. Having said that, let's see what we can do here to start implementing or extending this implementation to also support int and strings. So what I'm going to do that is I'm going to create some more internal stuff, right? So what I'm going to do is I'm going to create an internal comparable type because I'm going to leave the external comparable alone. It's there and it's there to extend any type, right, that you have control over. Now, Go does not allow you to add methods and basically extend a type outside of its package. So you can only really control types that you've created. You can obviously take third-party types and kind of wrap them, kind of like what we did here, right, in your own type, and then declare the method on this guy if you really want to store it. There's not much we can do about that here, but I can start supporting some built-in types that I know about, right? So what I'm going to do for that is I'll create a new type, which is the internal comparable. This is the private one, right? And this guy will wrap itself around any kind of value. Cool. And then basically I'll create a method on that comparable that more or less mimics the public compare. The compare that we've already declared in the data structures comparable. Okay, but this is going to support not just comparables, the public ones, but also int and string. So what we need to do first is figure out what our type is, our type being the receiver of this method, which is an instance of this guy. So we do, okay, switch c.value. And so this gives us the type of what this guy is holding, the actual runtime type. Cool. And then you can just basically do this. Case string. We'll have a case int. And really that's it. And we'll go ahead and implement those in a second. And then if it's not those two, I'm going to just assume it's a comparable. Because if it's not, then we'll go ahead and let Golang throw a panic because the person who passed whatever they passed in, they don't know what they're doing, right? And I cannot type, sorry. Right, so this doesn't have a value, this is just something that's just a pure value while you type, right? Okay. And then I essentially go ahead and return 2. I'm good, okay. So now what do we do here? So here we'll do basically something similar. Except it's going to be string. And in fact, I can just go ahead and copy this. And instead of comparable, it's string. It's string. Now string doesn't have a compare method, right? So we can say our last case is going to be greater than, because if C1 is less than C2, and this is kind of cool in Go. Not every language allows this, but you can just kind of compare strings straightforward like this, and this will do a lexicographical comparison, which ends up being, it's a fancy word for alphabetical, but also other things like numerical orders, all that stuff. So this lexicographical comparison happens, and so if C1 is less than, let's return -1. And since it's a return, I'll go ahead and do this in another if clause, which is if they're equal. And this, again, this is not like Java. This is not going to be a pointer comparison. This is actually going to compare the strings themselves, right? So this will actually do the right thing as far as string equality goes. And this returns equal 1. Awesome. And you kind of do the same thing with int, except this becomes int. And I could not figure out a way to kind of write this in a generic way here, where I could. There's a lot of duplication here, but I just could not get away from it because I need to make sure this is an integer comparison, this is a string comparison. So, and this is kind of what I was getting tired of. I didn't want to write a bunch of case statements to support every single type since I'm not really exposing this out. So I just picked 2 example types and I'm supporting them. I don't know if there's a better way to do it. Maybe I'm just not very skilled at Go yet. This is the best way I could figure out how to support this kind of functionality for multiple types. And I don't like it. I do not like it that much. This has been one of my complaints so far in Go. I'm trying to keep things simple. We're making them more verbose. So hopefully there's a better way to do this. And maybe I'll find out as I get better at the language. Or maybe this is one of the cons of using Go. Who knows? All right. So this kind of finishes out our compare. So basically this way we can compare ints and strings using this method on this comparable struct. And then basically I'll create a convenience function that allows me to kind of wrap things in there, right? So I'll create a, sorry, not a type, a function, which creates a comparable of this type, right? When you pass in whatever value, it just wraps around it. And again, here is where we kind of enter the stupidity. Right, so basically what I'm doing here is when I get this value, I'm just making sure it's a string or an int or a comparable. And if it's not, we're going to go ahead and panic. And I'll talk about the OK part there in a second here. I think that might be one of the first times we're doing that. In this tutorial here. Sorry. Sorry, not linked list, just comparable. Okay, so what this is just a kind of a painful way to go ahead and do sort of this type safety exercise, really, right? That when the value comes in, I make sure it's either a string, an int, or a comparable. And then as long as one of those 3, we go ahead and wrap it in our internal comparable. So we've got a comparable created here. And if not one of those 3, we create a panic, which will bubble up, just saying, hey, you don't know what you're doing. Read the documentation, essentially. I could, and this is in addition to what I was kind of ranting about earlier, I can't figure out a better way to do this. I wish I had a better way, because this is kind of getting verbose. This is the kind of stuff you want to stay away from. It's a lot of duplication of logic. But yeah, I just couldn't figure out how to really capture that, right? Especially without generics. Because if we could something like generics, we could bound it to a type, and here we could just do, okay, this thing's bound to a type. When you're passing me, is it of that instance? And you don't really have to even do that, because the syntax kind of should take over and be like, hey, we declared this thing to be of this, bound to be of this type. Why are you passing something that's out of bounds, right? And so this is something you have to do basically in absence of a feature like that. And I don't know how to really capture this kind of functionality in Go other than doing this. Maybe it's the wrong way to type a problem. But I just want to be able to support certain types out of box, to do this comparable stuff, so that the user can basically dictate, hey, this is what the natural order of the elements I'm throwing in the collection should be, right? Okay. Given that, I guess one thing we could have done is we could have passed some sort of a function that is not bound to any type. It just takes two interfaces, and you basically just define a function that this list can call anytime it needs to compare, and it's not really bound to type. That's another design decision I could have gone that way. I kind of orchestrated this example to show you what lack of generics can lead to if you're coding in a certain way. Okay, having said that, let's go ahead and update this add method now so it can leverage this new stuff that I created here. So here, instead of casting, what we're going to do, casting to data structures comparable, we're going to go ahead and do create comparable and throw the value over there. And this is now going to give me a comparable type, right? This guy. Sorry, this guy. So when that happens, the rest of the logic stays the same, right? We still want to check for this case. We're all good here until we get to this error, and I think we can get rid of that by just saying this. But we don't need this cast anymore, because this compare takes any type, and then it internally does all the type assertions and stuff, right? So if I hit save now, I think things should work, and if we did things correctly, our unit test should work, right? So we can come back here, and I'm not going to show HTML, let's just run this, and we actually fail. So if I go down here to my test, and so obviously this is the one that's failing, right? I want to make sure this still succeeds. So that actually runs. So what is the error here? I need some live debugging, right? Okay, so this is saying interface conversion is not data structures comparable. So the panic is happening on line 103. That is here. All right, so it's telling me that whatever is being passed is not a comparable type. And it's because we actually need to grab the value from here. I believe that's what the issue is, because before the comparable that used to be here was the actual value being passed. Now, when we're doing this create comparable, we're actually wrapping the comparable instance that is internal to this implementation around that value. So this thing is no longer the value, it's a wrapper around the value so that it can handle the different types, essentially, right? So that when we add it back into the list, we need to go ahead and access the internal value and get rid of the outer wrapper. So now, if we come out here back to our test and run this, we still fail. Okay, and so we're still failing, so we're probably still missing something in here. And that's right. So we actually insert into the list twice, or in two places rather. Here, in this case, but there's also this guy, and I need to assign, or not assign, but get to the value here again, so that we're adding the value every time and not the comparable. And that hopefully should do it. And that passes. Awesome. So our existing functionality still works. Let's go ahead and run our coverage. And now our coverage has actually dropped because we added quite a bit of code in there, right? So I've got more tests to write. So the only thing that's not covered here is sorted linked list.go, and it's dropped to 62.8%, which is really bad. At most, I want my coverage in the 90s. Sometimes you might not get to every single line, but I have absolutely want my coverage in the 90s. Really, you should be striving for 100%. And a language as simple as Go, probably always 100%, if not really high 90s. So let me write some tests so we can cover. As you can see, we're never even hitting the string case, never even hitting the int case, not really hitting these error cases, right? All right, so let's go ahead and write some tests for that so that you can get better coverage. Okay, so I've gone ahead and added tests to test string and int support as well. The test add string method, or the test, is very similar to the test comparable one that I created earlier. Basically, instead of having that whole person struct, it's just a raw string that I'm throwing in, but the names are the same, and basically the test ends up being the same, except for the fact that I put a little twist on it, and I use the iterator. And in fact, I use the reversible iterator with the flag set to true, so we're going to go backwards. And so we, basically go Zoe, Joe, all the way up to Adam, so reverse order. And, that works out to be good. And going through the whole thing, I'm also testing the hasNext method as well to keep returning true until we get to the last one, which is Adam. After that, it returns false. Awesome. And then test add int, similar, just some random numbers thrown in. And this one I use get again, and I should get in a pretty straightforward manner 1, 2, 3, 4, 4, 5. The only other test I added was this test add mix types. So this is where, again, having lack of generic support, we can throw in whatever we want. As far as the compile time goes, this is not an error. I added a 4, then I can, which is an integer, and then I can go ahead and add a string. The syntax doesn't care; it's allowed. We can pass in any type. Right? It takes an interface, right? But we should get an error when we go out and try to compare things, right? And that error will happen as a result of, let's see here. It will happen as a result of this compare method, in fact. When we try to do the switch, based on, if your first element was a string, it's going to call this comparable, and then it's going to try and compare string. But if your next one is an int, which is the type of this guy, then this downcast will fail, right? Because we are going off the type of the first type. So if you have mixed types, you're going to have a casting panic. And that's what we expect to see here. And so let's run this. If we run all the tests, everything passes. I come out here. I'm not going to show the HTML report because I'm confident we get 100% coverage across the board. And there's no reason to just go see green, right? So I think I'm done here with sorted linked lists. We're at a good spot. And just to kind of recap, the main focus as far as learning Golang was playing around with inheritance and polymorphism, right? So we saw how we can take an implementation that already existed, which was in linkedlist.go. Let me get rid of this stupid context highlighting. I'm not sure really how to get rid of that without doing something like that. And I'm not sure what's causing it. I'm assuming it's test coverage, but I have no idea how to get rid of it. Not yet anyways. But anyways, we come here in linkedlist.go. We had this existing implementation, and then we want to leverage as much of it as possible, but then just change the parts we wanted to, really here in the add portion, to tweak it so that now we don't hold elements in insertion order, but rather we hold them in a sorted order. We saw a bit of polymorphism because we're still exposing things out at datastructures.linklist, but now this guy has two different implementations. It has the base implementation where things are kept in insertion order, and now it has a new implementation. And so even though we expose things out of the interface level, it's the implementation that has been created by that, is the name of the game here. And even here you can see that this guy only really implements add. So when you're calling a get, or when you're calling a delete, or getting an iterator, all that stuff is still using this implementation. It's just the specific add logic that we have tweaked in our sorted linked list here to make sure at insertion time, after any given insertion, the elements are in their natural sorting order, not insertion order. Cool. So with that in mind, and with all that implemented, I think we're ready to start playing around with Go's concurrency, because I think at this point we've kind of covered all the other basics of Go, except concurrency, and what are all the concurrency primitives that Go comes with, which is kind of the exciting space of Go. So we'll do that by creating a concurrent version of the linked list, and going from there. And those tests are going to be fun. All right, so let's do that next.